Hello guys, welcome back to my Black-Scholes derivation video lecture series. This is going to be video 14, and this is going to be a very important video because we will be using Ito's lemma, a very important cornerstone of stochastic calculus, to essentially tailor expand in a multivariable setting our multivariable function for our financial derivative price, dv, as a function of s and t. So we'll be finding what this mathematically represents, right? And a few things I want to recall before I start off this derivation. I want to focus on S a little bit, and we talked about this in the past, about how to model a financial asset using geometric Brownian motion, and we did this as follows. We said that the differential of S is equal to mu s dt plus sigma s dw, and we've went over what mu and sigma represents many times before, but essentially what this is it's a continuous time stochastic process. And the reason we know it's a stochastic process and continuous times is because it's in differential form. But it's a stochastic process because we have this dw term, right? And just to make it clear, dw can be thought of as an infinitesimally small increment of the Wiener process or an infinitesimally small increment of Brownian motion. So those two are the same thing. And a key property in this is obviously the quadratic variation of Brownian motion, in which we concluded, not derived, but just concluded that dw is equal to the square root of dt, which can also be written as dw squared is equal to dt. Cool. And another topic that I want to brush up on that we discussed more recently is when we want to Taylor expand when we have a function of some kind of Brownian motion. We need, when we find df, we are going to need term 1 and term 2 of our Taylor expansion when we actually expand this out in this setting. And this term 2 specifically is because of the quadratic variation of Brownian motion. Cool, now that we got those out of the way, let's actually find dv in a mathematical setting. So let's start off with our Taylor expansion, which is pretty simple. We'll have dv is equal to the partial derivative of v with respect to s times ds plus our partial derivative of v with respect to t dt. And keep in mind, this is because our v is a function of s and t, resembling f of xy. So essentially, instead of df dx and df dy, I'm using dv ds and dv dt. And obviously, this is going to be our term 1. I'm going to add that with 1/2 times the second partial derivative ds squared with respect to our stock price, as well as our second derivative with respect to time dt squared, plus our second derivative of our financial derivative price with respect to our stock price and our time. And this whole thing is going to be our term 2 of our Taylor expansion. Okay, now I want to recall that ds actually has its own definition, which we've discussed in the past and earlier on in this video as mu s dt plus sigma s dw. Now let's plug that in. Hopefully I can fit this all in one line. If not, it's okay. I have dv ds times mu s dt plus sigma s dw, and all I did was replace this with my definition of ds plus my partial derivative of v with respect to time, and we just have time over here, so that's all well and good. Then for our second term, we have second partial derivative of v with respect to our stock price squared, and then we're also going to have mu s dt sigma s dw squared plus our second derivative of v with respect to t squared dt squared plus, and then I guess I'll write this on the next line because I'm running out of space, but we will have our partial derivative with respect to s and t times our mu s dt plus sigma s dw, and all of this is going to be multiplied by dt. So this is a lot longer representation of the same exact thing. All I did was replace every time I found my ds with my financial asset representation of ds. So that's why I have the term here, the representation here, and the representation here. Okay, cool. Let's keep going with our derivation. So we have dv is going to be equal to, we have a plus sign there, so we can expand this out, dv ds mu s dt plus dv ds sigma s dw plus dv dt dt. Cool, so that's our first term. Essentially, I just expanded this out to both of these, which is all well and good. And then let's work on our second term a little bit. The first thing I need to do, I forgot something here. This is 2 times that, right? Let's expand out this squared term real quick. So we have d squared v ds squared, and what this will turn into is going to be mu squared s squared dt squared plus mu sigma s squared dt dw, and if we square the last part, we will have sigma squared s squared dw squared. Cool, so that's all well and good. And then after that, I would also have that second term of my second term, which is d squared v partial t squared dt squared plus 2 times my partial derivative with v with respect to s and t. And I want to put this dt for both these terms, and I want to show you why in the next step. So essentially I'm going to have mu s dt squared plus sigma s dw dt, and that's going to be the end of my second term. Okay, pretty simple so far. Not really, but it's okay. Okay, so I want to note something down real quick. If I have dt to the power of n, and I say my n is greater than 1, then this would imply that my dt to the power of n is going to be equal to 0. And this is under the implication, or the assumption, that dt is infinitesimally small but close to 0. So it's not actually 0. That being said, we can note down a few things. We know that dt is not equal to 0. dt squared is equal to 0. We know that dw is not equal to 0. And this is because we can represent this as dt to the power of 1 by 2, which is not equal to 0. We know that dw squared is also not equal to 0, because this is this dt, which we assumed in this step is not equal to 0. And we have a few more combinations here. We have a combination of dw dt. Now this is going to be dt to the power of 3 by 2, and 3 by 2 is obviously greater than 1. Therefore, dt to the power of 3 by 2 is going to be equal to 0. So this is also going to be equal to 0. Cool, so what we're looking for is to cancel out any dt squared or dw dt. So our first term has dt, that checks out. Our second term has dw, that checks out. dt checks out. And then over here we have dt squared. So this is going to cancel out. dt dw, which also cancels out. dt squared cancels out. dt squared over here, which cancels out. dw dt, which also cancels out. Cool. So because this entire thing essentially goes to 0, 0 times any sort of derivative we get is also 0. This term is completely out, and the only part of this term which actually matters is going to be this. So let's rewrite the whole thing and see what we get. We have dv, which is going to be equal to our first term, which is all significant. Sigma s dw plus dv dt dt. Then we're going to add that with 1/2 times the only term in the second term Taylor expansion, which actually matters, which is going to be our d squared v ds squared, and the only term in this set that actually matters is going to be when it's multiplied with sigma squared s squared, and dw is just dt, so we can just write it as such. Cool, so this is a far simpler differential equation. Still a stochastic differential equation, or stochastic partial differential equation, because we have this stochastic term of the Wiener process or Brownian motion right there. And just to finish this off, I want to rewrite this in a little bit simpler terms just by combining all the dt terms. So essentially, in the end, what I have is dv dt, which I'm going to take care of this term right here without the dt, and then I'm going to say plus the derivative of my financial derivative with respect to my stock price, the partial derivative of that, times mean returns times s, which will take care of this term right here. And I also have my last term, which is in terms of t, so I can write that as 1/2 second partial derivative of my financial derivative with respect to my stock price times my volatility squared and stock price squared. And all of these are going to be my dt terms, and I have exactly one stochastic term, which is going to be my derivative of my financial derivative with respect to s times sigma s dw. And this is going to be the result of applying my Ito's lemma on geometric Brownian motion in the context of my financial derivative price as a function of s, which incorporates my geometric Brownian motion and time. So this is very important, and this is what dv mathematically represents right here. So very important little formula right there. And just to make things clear, this term right here has no randomness. Now this is a stochastic partial differential equation, so interpreting the geometry behind this equation is going to be very difficult, but just by looking at my differential terms, I know that this large term right here has no randomness, and this smaller term right here is going to be stochastic. So in the next part of our derivation, we're going to want to get rid of this stochastic element, because when we want a fair price for an option, we don't want it to be a probability density function. And in the next videos and the coming videos up until the end of this video lecture series, we'll discuss how to get rid of this stochastic element by incorporating a risk-free portfolio. Cool. I think thus far this sort of derivation has been the most complicated one. I recommend you guys to rewatch this video as many times as you need to, just to fully understand how Ito's lemma works. And just as a side note, Ito's lemma can be used on many different stochastic processes, not just geometric Brownian motion. And another note that I would like to make is that usually online, when you find derivations of the Black-Scholes, essentially what they'll say is you have a geometric Brownian motion, and then they'll just tell you to apply Ito's lemma, and they will end up with this equation right here in one step from our GBM. So hopefully this sort of step-by-step derivation of what's really going on has helped you guys in understanding how the Black-Scholes model works thus far. And that being said, we'll continue it and finish off the actual partial differential equation within the next few videos.